guys, I'm Munot and welcome to the School of Physics. So today we are going to do fluid mechanics in a very few minutes. So today's topic is fluid mechanics or fluid dynamics. Now fluid mechanics is a very good and easy topic. First of all, I'm going to tell you what pressure is. Okay, so as we all know, pressure is equal to force upon area. Force upon area. We'll take example of an hydraulic lift. So what happens in hydraulic lift? In hydraulic lift, we have car at one position. We have a car at one position. So mass of the car is mg, which is say F1. Okay, now we have to lift this car. We have to lift this car using R weight. Using R weight for equilibrium, and we fill a lot of fluid in it. We will fill some kind of a fluid in it. Okay, now for us to push this car, right? For us to push this car upwards, we have to stand here. Suppose you stand here and the force that you apply, the weight is F2. Okay, F2. Now the area of this surface is A1 and the area of this surface is A2. When you are pushing this car, so the pressure on both the sides should become equal. So we write F1 upon A1, which is the pressure, say P1, should be equal to F2 upon A2. This will be a direct question asked. So it will be asked, what should be, say, your force? The areas A1 and A2 are given. What should be your weight so that you can lift up a car of weight F1? Okay, so F2 then becomes F1 into A2 by A1. Okay, F1 into A2 by A1. So if you have lesser weight, this area A2 should be lesser. So the lesser the area A2 on which you are standing is, the lesser you will have to have your own weight so as to balance this car on a hydraulic lift. Okay, now I discuss two special cases, very few simple examples of motion of water in a cylinder. So suppose I have a tank with water, right? And now I accelerate this beaker with an acceleration a0. So what will happen? This water will change its shape to something like this. This was horizontal initially, now it has gone to something like this. Okay, so this angle is theta. Now we have to find, this is a very directly asked questions, it is very common question. You have to find what is the tan theta. So you have to remember this formula, tan theta is equal to a0 by g. No need to derive it, there are 2 or 3 equations that will be needed to prove this. So we have to directly apply this case in the exam. Another very commonly asked case I'll tell you is, suppose we have a beaker here, right? And there is water in it, and around an axis in the middle, we start rotating this beaker with an angular velocity omega. So what will happen? It will form a shape like this. Okay, and the water will rise to a height h, and here it will be the minimum height, and here again h. Okay, now the question that would be asked is, suppose the radius of the beaker is given r, the radius of the beaker is given r, it will be asked what is the height h if this is the situation. Okay, so here we have to remember a very direct formula, which is h is equal to omega square r square upon 2g. H is equal to omega square r square upon 2g. So this is the direct formula, this is what you have to remember. Okay, let's move to the next case. What is hydraulic what is hydraulic pressure? So hydraulic pressure is rho gh, where rho is the density, g is the acceleration due to gravity, and h is the height from the surface. So we have a fluid here. I am asking you, what is the, okay, so this is pressure by the atmosphere. Now suppose we have a height h1 here. Now the pressure at this point P1, the pressure at this point P1 is P1. So what is P1? P1 is P atmosphere plus rho g h. P1 is equal to P atmosphere plus rho gh. So this is the rho is the density of the fluid, g is the acceleration due to gravity, and h is the height from the surface. Okay, now the next thing that we have to remember is, suppose, what is this g? Suppose we put this in lift. Okay, we put this in a lift. We have put this in a lift. So this is my lift. Now I accelerate this lift with an acceleration a naught upwards. What will happen? G will increase. So this rho gh will rather become as rho g plus a naught into h, because the there's a pseudo force downwards. So there's this rho g plus a naught into h. Suppose we accelerate the lift upwards with an acceleration a naught, so the gravitation will reduce, and the gravitational acceleration will become g minus a naught, effective gravitational acceleration on the fluid. So this will become, when we accelerate the lift a naught downwards, this will become rho g minus a naught into h. Okay, so these are very few simple cases. Next I talk about what is the Archimedes principle, buoyancy, force of buoyancy, right? So not that buoyancy, that love the way you lie wala. We are talking about a different beyond force. Okay, so buoyant force. Suppose I have this block immersed in a liquid of density rho. Okay, and this is the volume of the block. This is the volume of the block which is immersed, say V, it is the volume of the block immersed inside the liquid. So what happens is, buoyant force is equal to weight of the liquid displaced. Weight not of the object but of the liquid displaced. So the density that we'll use, the density rho, will be not rho of object, it will be rho of liquid. Okay, so we write force of buoyancy. So there is this upward force buoyancy acting on it, and the force of the buoyancy is equal to rho liquid into volume V. Now what is this? This is equal to density into mass. Density is equal to mass upon volume. Density is equal to mass upon volume. So density into volume is equal to mass, and we are talking about, since we are talking about weight, so we add acceleration due to gravity g. So this is the force of buoyancy of any object immersed in the liquid, which is equal to weight of the object, weight of the liquid displaced. So we have to remember, this is a very common mistake which students make. Rather than using rho liquid, they use rho object. We have to use the rho liquid. Okay, next thing that we are going to see is equation of continuity. So what is equation of continuity? Very simple equation. Suppose I have this liquid. Can you see this? Is the marker not working? Okay, so suppose I have this flow. Here I have another. So this is a freely flowing liquid. This is my point 1. This is my point 2. Here the area of this hole is A1 and the liquid is passing from this hole at the velocity V1. Here the area is A2 and the liquid is passing at velocity V2. So equation of continuity says that A, that is area, into velocity of the liquid is equal to constant for a continuously flowing liquid. So A1 V1 is equal to A2 V2. So this is the equation of continuity. Okay. Now the next thing that we are going to see is Bernoulli's equation. Okay. Bernoulli's equation. So Bernoulli's equation, as we remember, what are the terms for kinetic energy? It's half mv square. What are the terms for potential energy? It's mgh, right? So rather than m, we'll use rho here, and then we'll also have an additional factor which is called pressure. So Bernoulli's equation says that pressure plus rho is the rho of the flowing liquid, rho half rho v square plus rho into gh is equal to constant. I'll draw and show, don't worry. So we drew something like this here, right? We drew something like this. Okay. Now from ground, this is the ground, and this is the height. This is the height h1, this is the height h1, this is the height h2, this is the area a1, this is the velocity v1, velocity of the liquid, area a2, velocity v2. Here we have pressure p1. Very simple question will come on the application of this Bernoulli's equation. If the pressure at point 1 is p1, what is the pressure at point p2? So what we'll do is very simple. P1 plus half rho is the density of the liquid, rho v1 square plus rho into g into h1 height is equal to p2 plus half rho into v2 square plus rho into g into h2. So very simple application of Bernoulli's theorem will appear in your exam. You just have to remember this Bernoulli's theorem. The next thing that we are going to talk about is the next and the last thing in fluid mechanics, Torricelli's theorem. Torricelli's theorem, or as you can call, velocity of efflux. Okay. So suppose I have this container here and it has a hole, and this is the container, right? Now the height of liquid in the container from above this point, taking this point as reference, from above this point is h. So this is the velocity at which this liquid is going out. This is the velocity at which this liquid is going out. So we have to find this velocity. We call this as velocity of efflux. So normally you have to just do it as root 2 gh, but in some cases there is also a comparison between the area of this hole and the area of the vessel. So we have to remember the formula. Formula says velocity of efflux is equal to under root 2 gh. Say this area of hole is A1 and this area of the vessel is A2. So root 2 gh upon 1 minus area hole, that is area 1 upon area vessel, okay, whole square. So in most of the cases area of hole will be very less than area of vessel, so this cuts out. But sometimes they also give a comparison between area hole and the area of vessel. So in that case we have to use this formula. Velocity of efflux is equal to under root 2 gh upon 1 minus area of hole upon area of vessel ka whole square, right? So friends, this was our chapter fluid mechanics. Very simple chapter, only a couple of formulas, you just have to apply them, majorly the Bernoulli's equation and the equation of continuity. Very simple chapter. I hope you'll be able to do it in exam. Thank you.